Hello, Pre-Calc BC, or technically Calc BC at this point. Today you will be watching a video on the derivative of a function. This is our first lesson from Chapter 3. And again, you are welcome to watch this video over spring break or watch it the first day back, and I'm happy to answer any questions you have as you go through it. So, alright, so let's talk about what the definition of a derivative is, because this chapter is all about derivatives, so, it'd be good to know what a derivative is. The definition of derivative is the slope of a curve, which can be found using the difference quotient. Ta-da! So here's the thing, we've already been finding the derivative. It's just the slope of the curve at a point, provided the limit exists. Because remember, sometimes your slope coming from the left and your slope coming from the right, or your limit coming from the left and limit coming from the right, are going to be different. If that's the case, we're not going to be able to find the derivative. This notation here, we'll say this f prime of x. This is another way to represent the derivative. When you see that, we're talking about the derivative of a function. We'll get into notation more in a little bit. The domain of f prime may be smaller than the domain of f. If f prime of x exists, we say that f is differentiable over that x. That means the derivative, or the slope, can be found or taken at x. A function is not necessarily differentiable at every point. So this is why the domain of f prime may be smaller. We're not going to be able to find the derivative at every point, which means that the function is not differentiable at every point. So now we're going to do number 1, find the derivative of f of x equals x cubed, then find f prime of 2. And this notation means that we're going to find the derivative when x is 2. Really, they're telling you that x equals 2. And we're going to do the exact same thing that we did before with our difference quotient. So we'll have the limit as h approaches 0 of f of x plus h minus f of x all over h. But again, x is 2. So you can choose to plug that 2 in now, or you can choose to plug it in later. It doesn't matter. You'll get the same thing either way. And now we'll go ahead and we'll plug this into the actual function, x cubed. So right now this should pretty much be what you're used to. Oops, that's a 2. 2 plus h cubed. So 2 plus h is going in place of x, minus 2 is going in place of x all over h. Alright, so basically for time's sake here, you would FOIL this 2 plus h cubed out, or you could use binomial theorem, or however you want to do it, but what you're going to end up getting is h cubed plus 6h squared plus 12h plus 8 minus 2 cubed is minus 8 all over h. You'll notice your 8's will cancel. And now all of this is divisible by h. So you can pull out an h and cancel it, or you can just divide by h right now. And you will get this. But h approaches 0. What's nice is that we no longer have a denominator, so all of these will go to 0, and you'll get that your slope, which is your derivative, is 12. So this is the slope of the curve at x equals 2. Your notation, we could say f prime of 2, the derivative of the curve when x is 2 is 12. Okay, just some notation for you. So this is really the exact same thing as before. We're just introducing some new notation and a new word, derivative. So there is an alternate definition of derivative at a point x equals a. So a is any number that you'd like. So this is another way to find the derivative. You'll notice that you're not using h anymore. We have the limit as x approaches a of f of x minus f of a over x minus a. So we are going to use the same equation as before, which was f of x equals x cubed, and we're just going to find f prime of 2 in a different way this time. Okay, we're going to use this new alternate definition. And it's completely your call in the future which one you decide to use. The original definition, which is your difference quotient, or the alternate definition. So, alright, so this is no longer as h approaches 0. Now, it's the limit as x is approaching 2. of f of x minus f of a, which is 2, all over x minus 2. Okay. Yes, you still need your limit notation. All right, f of x is just x cubed minus f of 2 is plugging a 2 in. Okay, and over x minus 2. All right, and now you may notice, oh, this is difference of cubes on top, so I can just go ahead and factor that. This will be x minus 2, x squared plus 2x plus 4. And look at that, your x minus 2's are going to cancel. And you've got this. Okay. And now you know that x is approaching 2, so we can go ahead, we can plug the 2 in, and you'll get 2 squared is 4 plus 4 plus 4. Okay, that's just plugging the 2 in for each of those, and oh my gosh, that is 12. So, again, f prime of 2 is 12. Again, this means the derivative or the slope of the curve when x equals 2 is 12. All right. Okay, so you may have noticed, oh, that seemed a lot faster. That was a lot easier. It's not always going to be easier. It really depends on the problem. So if you start the problem and you're like, oh, this is taking forever, maybe try it the other way. This one is an example where the alternate definition might seem a little more complicated because of your function. So we're going to differentiate f of x equals square root of x at x equals 3. We're going to use the alternate definition. So f prime of 3, that's what we're looking for, is, so you could have come up here and said f prime of 2. You don't have to, just practice the notation. Limit as x approaches 3 of f of x minus f of 3 all over x minus 3. The nice thing about the alternate definition is that you don't have any of these h's. I think it's a little easier to plug things in. This problem is kind of going to be a pain either way because you have the square root of x. Unlike above, you can't factor this, nothing cancels, so you kind of have to force this to cancel. Remember in Honors Algebra 2, one way that we manipulated an equation or an expression was to multiply by the conjugate. Normally we did that to get rid of the radical in the denominator. In this case, we are going to multiply by the conjugate of the top to manipulate this limit and see if we can get anything to cancel. Okay, so conjugate would be root x plus root 3 over root x plus root 3. So let's see what that gives us. So this is just something that you can try if you're like, what do I do with this now? This would be FOIL up here, and notice it's difference of squares since they're conjugates. So it would be root x times root x is just x. You'd have root 3x minus root 3x. Those will cancel. Minus root 3 times root 3 is just 3. And then on the bottom, I am not going to FOIL that out because what you'll notice is now your x minus 3's will cancel. Ta-da! Okay. So remember, we don't care if there's a radical in the denominator as long as when you plug in your number, you don't have a 0. So we can plug in a 3 now. And we will get 1 over root 3 plus root 3, which is 1 over 2 root 3, which you can rationalize or not. I'm just going to leave it like this. So this is the slope of f of x equals root x when x equals 3. Right? Or you could say f prime of 3 is 1 over 2 root 3. And again, no, you don't have to write that each time. I just want to make sure you know what we're actually doing. We're still finding the slope of the curve. We just have different notation now. So, all right, let's talk about that notation. Derivative notations, there are a lot of them. So you're going to see these constantly in different ways in the book, and the key thing is they're really the same thing. So this one here, you would call this f prime of x. All of these mean you're taking the derivative. Y prime, this is just how you say these things. This one, even though it looks like division here, that's just the notation. You would say this dy dx. Okay, it's just the notation. It doesn't actually mean it's representing division. And this doesn't mean it's representing multiplication. It's just that's how you say it, dy dx. This means the derivative of y with respect to x. Okay, again, all of these are the same thing. This one would be df dx, the derivative of f, meaning f of x, with respect to x. Okay, you could say it either of those ways. And then this one, this is especially fun. You would say this d dx of f at x. d dx of f at x. Or you could say d dx of f of x. And this is just the derivative of f at x. All of these are notations that you will be seeing. So get used to it. Okay, next. This could be the most challenging part of the lesson for some of you. We're going to graph f prime from f. The graph of f prime will always be 1 degree less than the graph of, there should be an extra f here, than the graph of f. Okay, meaning that when you're going to graph the derivative, because that's what this is saying, graph the derivative from the original function, the derivative is always going to be 1 degree less than the original function. So for example, this first function here, this is a parabola. It would have a degree of 2 in x squared. So when we graph the derivative, we will have a degree of 1, meaning our graph should be linear. Okay, our derivative will be a linear graph. This guy is an x to the 4th curve. Okay, it's that W shape, a degree of 4. So when we graph the derivative, it will be 1 degree less. It will be an x cubed. So that will look like a cubic. This is just helpful to know for when you're drawing these. Now you're still going to have to be a little more detailed than just drawing a line or drawing a cubic graph, but you at least know, okay, this is what it should look like. So here's the key thing here. You are taking this graph and you are looking at its slopes, and then you are going to graph a representation of the function's slopes. Okay, so you need to examine the slopes of this parabola. The big thing you want to look for is any time a slope is 0, and that's going to occur at the max or at the min. So the reason is because if you were to draw a tangent line there, your slope would be at 0. Okay, so that's the first thing I would do. So you can see the slope is 0 at x equals 2. Now, after x is equal to 2, as you go to the right, as x gets bigger, you're going to notice you have a positive slope. Positive slope. And because it's a parabola, as x gets bigger and bigger and bigger, your slope will get bigger and bigger and bigger, meaning the line will get steeper and steeper and steeper. So, or the curve will get steeper. So bigger slope as x increases. Bigger slope meaning more positive. Okay, the reverse happens over here. Okay, when x is less than 2, you have a negative slope. But again, as x gets more and more negative, as x decreases, your slope is going to get bigger and bigger, but in the negative direction. Okay, so I guess you could say smaller and smaller and smaller. I'll say a more negative slope as x decreases. So now we need to draw a representation of this. The key point was when x was 2. the slope was 0. So now your slope is going to be what you plot on this curve. The slope is 0 at x is 2. Okay? And as we went to the right, as x got bigger, your slope was positive. Okay? As to the right of 2, the slope was positive. And as we went to the right further, the slope got bigger and bigger and bigger. Meaning you have a positive slope that's getting bigger and bigger and bigger as x goes to the right. Notice positive, meaning I have drawn this in the positives. Okay? Whereas when x is less than 2, the slope was negative. So now your slope is in the negatives. Again, this is the graph of the derivative. Okay? So this is saying the slope was positive when x was greater than 2. The slope was 0 when x is equal to 2. The slope is negative, okay, because we're in the negatives down here, when x was less than 2. Notice that the y-coordinate here is getting bigger and bigger and bigger as x goes to the right. That's because the slope was getting bigger and bigger and bigger as x increased. And again, we also needed it to be a linear graph. So this represents that. Okay? All right, feel free to stop the video and call me over and ask me about this. I know that it's very abstract. So let's try another one. Start by finding your max and mins. That's when the slope is going to be 0. So that would be here, here, here. Notice when you just draw a tangent curve, it's straight across. So you've got, that's my dog rubbing on the carpet because she's a weirdo. So you've got something in the negatives. Penny, knock it off. 0, and then something in the positives. I didn't give you numbers here, so it doesn't need to be exact. So that's where your slope is 0. Okay, so slope is 0 at 0. Slope is 0 a little to the right. Slope is 0 a little to the left. Okay, so now let's see what happens in between all those points. So here, all the way to the left, what type of slope is that? Well, it's negative, right? That's a negative slope. Meaning that to the left of that 0, your slope will be down in the negatives. Okay, this is in the negatives, and that's as x goes to the left. That's why I have this arrow going to the left. All right, what about in between these two zeros? See how there was a horizontal line here and here? So what's happening in between those? Well, in between those is a positive slope. See how that line's going uphill? I'm running out of room. Positive slope. Okay, which means that in between these two, it's got to be positive. But remember, then it's going back to 0. Okay, so we're kind of figuring out how to connect these dots. So positive. I also know, remember, this is going to look like a cubic graph, so that kind of tells me that this needs to come here. The reason it comes back down is because then look at this next part. Between these two zeros, that little section is negative. Okay, so it's got to go back into the negatives. And then, well, you've got that one last 0 right there. What happens after that? As x is bigger than this point right here, this slope is positive. Okay, so here your slope is negative. We're going to be back in the negatives. But then it's got to come back up because after that point the slope is positive again. Positive meaning in the positives of your y-coordinates. And if you look, that does match a cubic. So let's run through that one more time. So now you can see how this matches. Okay. So slope of 0, slope of 0, slope of 0. All I did was I kind of brought up where would that be. That's where I put my 3 dots here. Again, it doesn't have to match perfectly. So now you care about, well, what's happening in between those 3 points. Well, I'll call this point 1, point 2, point 3. 1, point 2, point 3. So it's a little easier to describe. To the left of point 1, you have a negative slope. Negative slope. That's why we are in the negatives here. Okay. Between points 1 and 2, this is a positive slope. But between points 2 and 3, it's a negative slope. So that's why between 1 and 2, we are up here in the positives. But 2 and 3, we are down here in the negatives again. And then to the right of point 3, your slope is again positive. Okay, so I'm back in the positives. Again, we have to match that our degree of f prime, which is this guy, will be 1 degree less than the degree of f. Okay, so we have 2 more. Next, we are going to sketch a graph of a function that has the following properties. F of 0 is 0. The graph of f prime is given below, so we're kind of going backwards this time. This is f prime. We're going to go to the original function. And 3, f is continuous for all x. So again, that means the left-hand limit is equal to the right-hand limit, which is equal to the f of, I'll say, a. All right, so what do we know? Well, if f of 0 is 0, we know that we go through 0, 0. Okay. Ta-da. All right, we have a point. Let's look at the graph of the derivative. So it looks like as x is greater than 1, remember this is representing what your slope is. So when x is greater than 1, your slope is 2. Okay, because we're at 2 here. A constant slope of 2. All right, and I know it's constant because even as x increases, the slope is still at 2. Constant slope. Okay. But as x is less than 1, the slope is down at -1. Also constant, because notice it's still at -1 as we are going across. The slope is not getting bigger or decreasing like it was here. So here your slope was getting bigger and bigger and bigger because the slope is getting bigger and bigger and bigger of this curve. But this is showing the slope is staying constant. So we'll have to think about what that means. All right, and then f is continuous for all x. Continuous meaning we're not going to have any jumps, we're not going to have any holes, we're not going to have anything like that because we're continuous all the way across. So, all right, let's see how to do this. If x is greater than 1, the slope is 2. Okay. And if x is less than 1, the slope is -1. Well, let's start with this one because we know that we've got a point at 0, 0, and 0 is less than 1. So let's begin there. When x is less than 1, the slope is -1. So here's x is 1. And if we have a negative slope here, we have to have a dot here because that shows that we've got a negative slope, a -1 slope that is still going through 0, 0. Okay. Again, we know we're going through 0, 0, but we also know that at that point you have a slope of -1. So that kind of helps me to figure out the rest of these dots. I'm going to draw an arrow that way. Okay, so -1. I don't know why I just didn't make a negative. M equals -1 when x is less than 1. All right, well now when x is greater than 1, the slope is 2. So at 1, greater than that, my slope is 2. 2 over 1. 2. So m is equal to 2 when x is greater than 1. Notice that I have a closed dot here. It has to be a closed dot because the graph is continuous. If you had an open dot, that would be a hole. We would no longer have a continuous graph. Okay, so that does have to be a closed dot at the vertex. Now, why are these open dots? Well, that's going to get more into what we're going to talk about tomorrow, that the derivative doesn't exist in case the slope coming from the left and the slope coming from the right are the same. And as you notice, on the left your slope is -1, on the right your slope is 2. So technically, this is a little prequel of what we're doing tomorrow, the slope or the derivative doesn't exist at x equals 1. Because at x equals 1, you're a part of two different slopes here. That's why these are open dots. We'll get more into that tomorrow. But there you go, that's that graph. All right, and the last one. Given that f prime of 3 is equal to -2 and f of 3 is equal to 7, we're going to write an equation of a tangent line and a normal line. So this is actually not difficult. You just have to be able to interpret the notation. This is saying that when x is equal to 3, the slope, because that's what f prime means, is -2. And f of 3 equals 7, that means you have a point at 3, 7. So look, you have everything you need. You have a point, and notice x is 3, x is 3. You have the slope at that point. So, I mean, that's all you need. Tangent, we'll say y minus 7 equals your slope was -2, x minus 3. Normal, as we know from our last unit, you have to take the opposite reciprocal, sorry, speaking is hard, of your slope. So your new slope will be 1/2. And that's it. So there you go. Hopefully that was helpful. Again, please feel free to ask me questions about this, and I will see you tomorrow. Bye.